All right, so last video we talked about just one-dimensional collisions. This video is collisions in two dimensions, which it's pretty much like all of our things in two dimensions. We're going to split it up into X and Y components. All right, that's the main gist of it. So when we have a collision that's not head-on, the masses don't end up traveling along their initial axes. So it might like glance off like this, or maybe we have something that, and then they go off at an angle like this. So in this case, we have two dimensions. We don't just have one dimension. So two-dimensional collisions in a closed isolated system still have their linear momentum is conserved, but again, it's going to be conserved in both the X horizontal direction and the Y, well, might not be vertical, but you guys know what I mean. So it's going to be conserved in all of our different dimensions that we have. If the collision is elastic, we also know that the total kinetic energy is conserved as well. So we have the initial momentum of the system, initial momentum of object 1 plus initial momentum of object 2 will equal the final momentum of the system, final momentum of object 1 plus final momentum of object 2. Of course, this is only for, this bottom one is only for elastic collisions. That is when we have conservation of kinetic energy as well. So what we do for these problems is all we're going to do is split up the velocity vectors into X and Y components and then use conservation of momentum for X and Y separately. So we can see here that we have a conservation of momentum in the X direction. So momentum initial of object 1 plus momentum of initial in the X direction of object 2 equals momentum final of object 1 in the X direction plus momentum final of object 2 in the X direction. And then of course we just plug in mass times velocity in for each of these momentums. Notice how the velocity vector is the one with all of those crazy subscripts. We have velocity 1 initial X direction because mass is not a vector, right? That doesn't have X and Y components. It's just a scalar quantity. So because of that it's velocity that we're splitting up into X and Y components. So here's our X direction, here's our Y direction, and it's as simple as that. We then just take them separately, and then at the end we might put them all together depending on what exactly they're asking for here. They might ask for unit vector notation, they might ask for magnitude angle notation. If they do ask for a magnitude angle, of course we have to then use Pythagorean theorem and our trigonometry in order to find the magnitude of, say, the final velocity and the angle that velocity is at, or something like that. So just like we treat any other two-dimensional problem, we can also do this with conservation of momentum.